Are we ready? So it's not okay. That's right. Okay. So welcome everybody to the last day. The people who are brave enough to maybe see the typhoon. We're very happy to have here Jens Eisert. He has had many contributions in condensed matter physics and the intersection with quantum inflow. And he'll tell us about potentials and limitations of near-term quantum computing.
Yes, thanks so very much indeed. Good morning, everyone. Thanks for the kind invitation to this wonderful conference of the TQC series in this splendid location and this hideaway location in the middle of the Pacific Ocean. So let's see how it goes with the typhoon over the weekend. Maybe we all get stranded and stuck here, and then we start a new life and a new group here. That wouldn't be the worst of all worlds. But seriously, when I was asked to give a talk here, I was wondering that it may be a good idea to meditate a little bit about the state of affairs in quantum computing and discuss the potential, but also some of the limitations of quantum computing as we will have it soon or in the near future. After all, quantum computing is not a new idea. Already in the 1980s, Feynman, Benioff, and Deutsch were contemplating what would happen to notions of computing if the constituents, the single carriers of information, were like single quantum systems. The big splash came in the 90s with Shor's algorithm that's presumably still the most powerful algorithm we have today, for better or worse. But only as recently as, well, a bit more than 5 years ago, protagonists actually set out to build such devices to a reasonable scale, and we now have superconducting devices with over 1,000 qubits. There was a big splash with arrays of neutral Rydberg atoms just before Christmas, but there's also a couple of other architectures. That's great. I mean, of course, these devices still fall short of being full fault-tolerant Shor-class quantum computers, yes, but at the same time, it's true that such devices seem completely inconceivable not very long ago and were in the utter realm of science fiction. That does generate an interesting state of affairs, yet the make or break question, the elephant in the room, is the question whether we can hope realistic devices, again, of soon and the near future, to have some sort of speed up over classical computers. Now, for very much paradigmatic problems, this seems to be the case. And the most paradigmatic of all problems is we just go into the lab. That was a joke. Never let a theorist into the lab, but somebody else goes into somebody else's lab and just takes raw data. And then following the Born rule of quantum mechanics, you always get new outcomes. Even if you repeat the same experiment over and over again, you get some distribution. And there are some settings which are pretty boring and give rise to pretty boring and pretty flat, actually close to uniform distributions. Yet their tails are so funny and intricate that it's not so easy to classically sample from a similar distribution, or slightly more precisely put, sampling from a distribution that's close to the right distribution in the total variation distance is computationally hard under reasonable computational complexity assumptions. So this can not only be done, but this has been done to great publicity. There was experiments by the Google team, but also the Tianwan team in China in the lab to like enormous attention. That's great, and it also sharpens the mind in a good way of what it means to have a quantum advantage in a paradigmatic setting. But there's also lots of intricate and funny fine print, if you want. We just put out a review article on that not too long ago in the RNP, and there's a number of funny aspects of this. Say, verification is not so easy. People usually do something like linear cross-entropy benchmarking, which is sample efficient, but computationally inefficient to build trust in the correct functioning of the device. At the same time, it's true that you cannot black box verify such machines, so that you cannot test based on data alone whether they've done the right thing, or you cannot, there's no property testing algorithm that's sample efficient that would witness the closeness in the right sense to the anticipated distribution. It's kind of a bit funny. You have this super powerful device, but you cannot verify that you're actually doing the right thing, or you cannot discriminate this from a not so powerful device, which generates an interesting flavor. If you have trust in the functioning of your quantum measurements, though, you can do something about this. And there are some settings, in fact, we discussed this yesterday over a poster and at the poster session. If you have trust in the functioning of your quantum detectors, you can take measurements in some settings, and based on those measurements, you're not building trust in principle functioning of the device, but you can really basically bound the total variation distance to the right distribution from measurements alone. And then you say, I'm right. And they say, yeah, good, but what is it? What comes out? You have to go into the lab, you have to take the data, but based on measurements, you can infer that you have done the right thing and that data are nearby in precisely the right sense. So it's kind of an interesting state of affairs that you can make predictions about the correctness of something without being able to generate efficient samples from the right distribution. So here we joined forces with a team of Rainer Blatt and others in Innsbruck, and we recycled qubits in the setting, which is kind of a cute thing in its own right. So this is encouraging. So there are prescriptions where there is reasonable hope that quantum machines do something better than classical computers on mathematical well-defined tasks. That's nice to see, good to have. At the same time, these are not really applications of any meaningful type, right? That begs for the question, what next? And the answer to this question very much depends on who you ask. When you ask more physicsy people, they will talk about readback atoms in arrays. When you talk to more computer sciencey people, they want to see applications that are maybe more, well, at least in spirit, industry relevant, maybe about problems in machine learning, optimization, quantum chemistry, or whatnot. And indeed, in the first part of the talk, or in the first part of the remaining part of the talk, we will have a look at the good part, the good things, and look at applications in machine learning and optimization. This will be somewhat superficial. I go over a couple of insights, and then we see what to learn from that. At the same time, recent years have shown that we should expect limitations of near-term computing in the absence of quantum error correction. In a way, if you don't do correction and you have like depolarizing noise along the way, you're kind of sinking into the ground of noise, and you should expect, say, at polylog depth to be close to a maximally mixed state for isotropic noise, or at log depth already in the Gibbs sampleable ball, which is great, but then you're not expected to have a quantum advantage over a classical machine in some way. So there's some limitations that we have to live with, that we are better carefully and wisely aware of. And this is also the topic of the second and longer and more or less superficial part of the talk, where we look at limitations in learning a bit, and a lot more on error mitigation and for non-unital noise. That's the bad and the ugly, and at the very end of the talk, there's the showdown between the good, the bad, and the ugly, and we will see who will win in the end, or you judge for yourself. It's all up to you. So that's the plan for this talk. Very good. The good. Applications in machine learning and combinatorial optimization, question mark. Now, it's very difficult to deny that machine learning is changing the world we live in. ChatGPT is virtually everywhere. Even the title, the picture with the glass on the title page, I did with a machine learning image generator. It's, well, ubiquitous in our everyday life, for better or worse. There's also loads of scientific applications, say, when it comes to the study of quantum materials or quantum chemistry, where machine learning is basically totally commonplace these days. And given the ubiquitous success of machine learning on the one hand, and the insight that quantum algorithms provide speed up for highly structured, well-defined mathematical problems on the other side, it makes a lot of sense to see or to think in what way there is scope for quantum-assisted machine learning in one way or the other. So what does that mean? In the perfect world, we would like to have rigorous guarantees for state-of-the-art learning algorithms applied on real-world data sets. So data sets like handwritten notes, pictures of cats and dogs, to which an algorithm is being applied, stochastic gradient descent, expectation maximization or so, on a model, say neural networks in the classical realm or parameterized quantum circuits in the quantum realm. And then you want to do something better in the quantum world compared to the classical setting. This again can mean many things. You can think of having a learning algorithm and looking at fewer pictures of cats and dogs. So you look fewer samples, that would be an advantage in sample complexity. You can do better, faster in a way. So the algorithm could work faster. That would be an advantage in computation complexity. Or you could think of generalization bounds for unseen data. So these are all different notions in which you can hope a quantum machine to do better than a classical computer in meaningful machine learning tasks. So are there quantum advantages? So yes, there are in several ways, and I will kind of go over a couple of notions along these lines. So in particular, there's a quantum advantage in packed distribution learning, where you think of a generator that produces samples from a given distribution. You take like seed randomness, and the generator is spitting out samples from a given distribution called concept class in this context. And the task of the learner is to take these data, to look at pictures of cats and dogs and to meditate, and then to spit out new pictures of cats and dogs, or generate samples from a similar distribution. That's generator learning, or learn the distribution as such in density modeling. So the fine print here is, there's several fine prints. A most meaningful kind of mathematical precise notion of that kind would be that of probably approximate correct learning or PAC learning, where a distribution class is efficiently PAC learnable with respect to some distance if there's an algorithm which for every distribution in the concept class and every epsilon and delta, given access to an oracle, careful, oracles are dangerous, so that's not a Q-sample oracle or some oracle that hides lots of computational power. That's just a classical oracle that would take classical data that you can write on a sheet of paper or have in your brain or in desktop computer. It's just taking classical data or quantum data. And that outputs in time polynomial and all the parameters with probability at least 1 minus delta. So probably samples from a distribution that are close, say, in this distance, Kullback-Leibniz or so is approximately correct. You stare at pictures of cats and dogs and you kind of generate pictures that are close to cats and close to dogs with high probability. That's kind of PAC learning. And indeed, for that type of PAC learning, both in the generator sense and the density modeling sense, there is a super polynomial quantum advantage. And as you might imagine, when you prove such a thing, the more difficult thing is not so much to think about the quantum algorithm, but to show that the classical part is difficult. And here we stand on the shoulders of giants, or rather the shoulders of kerns in this case, who looked at certain families of pseudo-random functions that cannot be discriminated from uniformly random functions by polynomially constrained observers, to then generate distributions that start from actual randomness and append the output of a pseudo-random function to formulate distributions that are hard to learn by any classical learner. So the fine print comes along with actually generating these pseudo-random functions with Goldwasser-Mikali trees, and the quantum algorithm basically amounts to walking this tree backwards and to crack the hard-to-learn distribution in a way to then give rise to a super polynomial advantage of the quantum learner over the classical learner. To be fair, this is like for completely abstract synthetic data. It's kind of a reverse engineered setting. There are no pictures of cats and dogs involved or handwritten notes. It's an in principle result. There was a similar result by the IBM group coming out at a similar time, motivated by similar types of reasonings, and it requires a fault-tolerant quantum computer. But then it's good news that there is an advantage. So there are meaningful learning tasks for which one can prove a super polynomial separation of the quantum over the classical learner. That's great. But if you want to think of more practical data, you have to go in other directions. And this is something we came up not so long ago with the team in Chicago, where the first 3 authors are called Liu. They're all more hyper than I am, which is something, but they're all not related. And what we thought of is to think not of quantum learners, but to think of training of classical networks, of sparse, pruned, large-scale classical networks with new variants of HHL algorithms that have a super polynomial advantage over families of classical training algorithms, including stochastic gradient descent. So it's not about so much about quantum learning, but to use quantum algorithms to train large-scale pruned classical networks And this is a relatively short paper with like 40 pages or so of appendices where we carefully look into the data uploading so that it's efficient, there's no QRAM involved, and that all the fine print of this algorithm can be made sound and precise. And the nice thing about this is that this really works for classical and natural data. We couldn't resist on applying this to the CIFAR 100 data set, which is like one of these industrial style data sets for machine learning that also does include handwritten numbers and pictures of cats and dogs, and for that matter, which show the functioning of the approach also in a more like practical mindset, if you want. This picture is not from the data set, but that's actually our own cat. I made it a habit to every morning get up at 4 in the morning to get up, have my coffee on the table and put up my laptop. And then the cat also gets up at 4 and sits on the laptop and looks very smart. And so sometimes puts the claw into the coffee and zips on it, but doesn't like coffee. And also no cat was harmed in the making of this talk. So that's how we do it in our household. Anyway, that's nice. It also requires a fault-tolerant computer, but this is a kind of a different reading in which we can hope a quantum algorithm to solve a task that is related to a meaningful machine learning task. What we are also working on these days is to think about quantum advantages of near-term machines, near-term algorithms, where we think of advantages of constant depth quantum circuits to constant depth classical circuits with bounded fan-in gates, where you can show a separation again. That's again for classical and artificial data, not very natural, but this is for a kind of a near-term quantum computer because it involves only like a constant depth quantum circuit of a kind. So you see, we're kind of approaching the real thing from different angles and different sides. So the true real question, namely, is there an advantage in meaningful learning tasks that in the near-term regime? We don't have this yet, by no means, but we're kind of trying to come from all sides to come closer to the aim here and making some progress along these lines. Is there an advantage in combinatorial optimization? And this is a question that's much discussed these days, also for better or worse. There's a bit of a hype involved. Like in the popular press discusses this a lot. There was a big European journal for like industrial matters that had on the title page, quantum computers can solve all questions faster. It's like, whoa. I mean, no. I mean, the marriage problems of my neighbor are not solved. And nor are all optimization problems. Common optimization problems of a combinatorial nature are NP-hard problems in worst case complexity, which means that, well, a classical computer cannot solve all instances of polynomial time. Yes, but it also means that a quantum computer cannot solve these problems in polynomial time either. So what's even at stake here? So in what sense can a quantum computer do better in problems of combinatorial optimization, say let this be of a traveling salesman type, Kubo, integer, linear programming, you name it. And at least this kind of conceptual question was something we were interested in and wanted to make progress, and we did with a result on integer programming that's also presumably technically interesting in the carb reduction that we propose, asking in what sense are there quantum advantages. When we looked at advantages in integer linear programming, so linear programming with integer valued objective functions, where we found a new kind of polynomial reduction using Occam's razor and computational learning theory applied to the formula coloring problem, going all the way to integer programming, which is kind of technically interesting in its own right, I presume, where the hardness is only making the assumption of the hardness of inverting the RSA encryption function. That's the only assumption we make, and based on that, we can show a super polynomial separation in the sense that there are some instances that are hard to approximate on a classical computer, whereas they can be well approximated in polytime on a quantum computer. So the hardness, easiness kind of region is shifted. Some instances, approximating some classically hard instances can be done well on a quantum computer. Again, these are artificial instances, but this is an explicit carb reduction if you want. So there's also a master student just contemplating about this explicit instance that we have and seeing what structure is there in the problem. That's again for a fault-tolerant quantum computer, but you have to start somewhere. At least this kind of qualifies the sense in which we can hope quantum computers to have an advantage in these somewhat practically minded optimization problems of a sort. So to cut a long story short, this shows that in a way there are advantages, like proven quantum advantages, proven separations in interesting learning and some optimization problems. They are not really industrial problems of a kind yet. I mean, that is not the case, but at least these are problems that have a feel of the real thing, that kind of produce some sort of input to the question whether we can reasonably hope quantum computers to have an impact in practically minded problems in machine learning and optimization, providing some progress along these lines. And that's quite hopeful. There's things we can do something. So a quantum computer can do better than a classical computer on meaningful problems of this kind. That's encouraging, makes me hopeful. I see many fresh faces here this morning. It's also interesting when you go to a different place, it's interestingly correlated with people here that are attending. Good. That makes us fresh and hopeful in this morning. That said, let me turn to the second part on the bad and the ugly, on limitations on non-fault tolerant quantum computers. That's also something we thought quite a bit about recently, on where this all ends. In particular, when we thought about limitations, we thought about limitations of learning problems, picking up the thought that we just had some time ago. It's good that there's some very structured problems where there's a quantum advantage, but usually when you think of quantum machine learning, you think of variational quantum algorithms where there's a quantum circuit in the center with knobs, with parameters. You take data and there's a classical algorithm surrounding it that would control this quantum algorithm based on the classical data that you have. You have many rounds, and you would think of a training of a quantum circuit based on data estimating gradients or so. And you could ask, is there an advantage in learning problems of this kind when you think of, well, restricted Boltzmann machines, variational algorithms or so along these lines? Yet that's not so easy, because it's not so easy to capture mathematically such complicated prescriptions. So you need a vehicle to make progress along these lines, and we thought quite a bit, although I will not say so much about this today, on the question whether you can actually learn the output distribution of a short quantum circuit. You take a circuit and you measure and you say, can you actually learn the output distribution in the Pak sense, both in the generator modeling or the density modeling sense? And this is kind of interesting, and that actually gives rise to a hilarious crime story of the first leak, and with ups and downs and manic depressive phases along the way. For example, it turns out that already for a bit longer than constant depth circuits, you cannot learn the output distribution from samples alone in the Pak sense. For the SQ oracle, so that's an oracle that's basically producing outputs that are promised to be near the expectation values, already at log depth, you cannot learn the output distribution of a short quantum circuit. Not even a quantum computer can learn its own output distribution. Kind of interesting and somewhat shocking, but learning the output distributions of that kind can be hard once you've measured in the computational basis and have produced classical data of a kind. So this is the question of, can you Pak learn the output distribution of quantum circuits? There's yet some circuits for which you can learn the output distribution efficiently. These are, unsurprisingly, Clifford circuits. So one can actually learn efficiently, both sample and computationally efficiently, learn the output distribution of Clifford circuits, which may be natural, but it's not as trivial as you might think, because there's still many Clifford circuits. But the Clifford circuit output distributions are uniform over affine subspaces, over finite dimensional vector spaces. And then you can make a Gaussian elimination variant over finite fields to kind of learn the distribution. So learning the output distribution of Clifford circuits is easy, so to say. Now we know that if you have a Clifford circuit, you can upgrade them to universal circuits by augmenting them with T-gates. So that's the mother, father, diverse of all universal circuits, so the Clifford plus T-gate setting. So the question is, if you add T-gates, then things become universal. So how many T-gates do you need to add to make a Clifford circuit unlearnable? And then we look at this question, and to our surprise, we found that if you take a T-gate, here it is, and you place it into the circuit, then you get a hard-to-learn distribution from a single T-gate. So a single T-gate renders learning hard, which is based on a learning parity with noise problem. I mean, the noise is the gate. There's no actual noise, but in the polynomial reduction, that's proven in this fashion, which is kind of interesting when you think about this, because clearly you can still simulate the machine, both in the strong and the weak sense. I mean, wow, what's a T-gate? It's a superposition of this and that. You simulate both and put it together. How hard can that be? That's actually true even for log many T-gates, but you can't go back. Once you have the gate, you cannot re-infer what you've done with the T-gate, and learning the output distribution of a single T-gate is hard. That actually turns out to be remains average case hard. I saw the first author of this paper also somewhere in the back. I don't know. So yeah. So that's kind of average case hard. It's kind of one of the few average case hardness results that you have available. That's kind of cute in its own right. So that kind of gives an interesting flavor to the question what T-gates do to quantum computing. One day I will give a talk on a cup of tea, or the power of T-gates in quantum computing. Here I mentioned something else. Maybe I have the time to briefly mention this. It's kind of cute. You know what a unitary design is, right? That's a collection of unitaries that resembles the Haar average. A unitary K design is a collection of unitaries that give rise to the right kth moment compared to the Haar average. And you also know that random Cliffords just so fail to be 4 designs gracefully. They're a bit of 4 designs, they're 3 designs. So how can you upgrade a unitary 3 design by Cliffords by T-gates? Take 1,000,000 qubits, I wish, and I want to have a 17th order design. How many T-gates do I need to add with 1,000,000 qubits to get a 17th order design? Maybe 5 or so. It turns out that the number of T-gates you need is constant in the system size. And then this kind of universality seed amplifies over and over again and spreads over the 1,000,000 qubits to get a 17th order design. That's kind of funny. So it's a very technical result. When we put out the archive, we called the paper Quantum Homeopathy Works, because the medicine of the T-gate can be amplified over and over again. It never stops. We didn't dare to put this into the CMP. That's a German publisher. They have to be very serious. But we also got very hilarious emails following this archive submission by lots of people who said, oh no, you show how quantum healing can be done. But on a technical level, this is kind of interesting as it shows the intricate power of T-gates in quantum computing in a way. So far, so good. This is for noise-free gates, even though there was parity learning with noise involved, but it's not actual noise. That's fake noise, but I mean, the biggest enemy in quantum computing is real, factual, and actual noise. When we think of quantum circuits, that's not what we are doing. We are doing something else when we have a quantum circuit to get expectation values or samples. We are realizing something like this: a noisy circuit that is not doing the right thing. Or a common model is like this one. You have a perfect circuit that's interdispersed with little channels, for example, depolarizing channels, non-unital channels. There could be, say, a depolarizing noise with some parameter that captures how depolarizing the noise is as a good model for the real thing. In fact, I've seen this model a couple of times. Yesterday at the beautiful poster session, we talked about this here and there, actually, a couple of times. It's like, sometimes I call this the Volkswagen of the noise models. It's just so plain vanilla. Actually, recently I gave a talk on quantum error correction. I was referring to the toric code as the Volkswagen of the quantum error correcting codes. And the speaker after me was talking about error correction. And then, about machine learning, and had a collaboration with a car manufacturer. And then he was talking about a collaboration with the toric code of the car manufacturing industry. Oh, that's somewhat funny. Anyway, so there's a common model for for quantum computing, you do a perfect circuit, interdispersed by noisy circuits, say depolarizing noise, and you say, can I do quantum computing with that? How far does that go? How detrimental is noise? And can you undo the noise? And the sad truth is you can't. It's quantum noise. It's there. To stay, you cannot undo quantum noise. But you can try, right? And that's the task of quantum error mitigation. That's more than one protocol. It's like a family of protocols that take data and largely on the classical level try to undo as much as you can of the quantum noise with classical signal processing methods. For example, it's often much easier to add noise than to subtract noise. I wish, right? But you can add different noise levels, and then you take data at different noise levels, and then you can use sophisticated extrapolation methods to extrapolate to zero noise, and then take this value here. That's a pretty cool idea. It's called zero noise extrapolation. There's also other methods like probabilistic error cancellation that are using largely classical data to infer what the experiment would have been without noise. It's bread and butter in the quantum computing world. It's central for the IBM computing strategy. These are interesting tools that are routinely used in basically any reasonable near-term quantum application to undo, say, some of the measurement noise or so. These are very practical and important tools. What we thought was, how far does this go? So, I mean, how does this scale in resource? Of course, this can and should be done, but what's the sample complexity overhead you ultimately need to have in worst case to perform error mitigation of a kind? And this we looked at. There were some bounds of that kind already available. We looked at this in a kind of fresh way with new tools. I mentioned some of them to see how far this can be pushed. And to start with, we kind of formulated a framework, a mathematical framework of error mitigation that's large enough to encapsulate most of the tools that would reasonably be called quantum error mitigation in the standard sense. So it captures large class of protocols. You have a noisy quantum circuit, as I've shown here. You take data, and there's a kind of a classical algorithm afterwards where you want to produce approximations of expectation values based on data of the kind that you have. And you ask how well this can be done, how many samples do you need to make it all happen? Or more precisely, like we formulate this as a kind of statistical inference problem, like a kind of a learning problem, in terms of the relevant parameters of the problem. So the circuit depth, d, the circuit width, n, and parameters like the depolarizing noise parameter or similar quantities for non-unital noise, and ask how well can this work? Or in other words, what are the resources you need to make it happen? How many copies of the noisy state sigma prime are actually needed to estimate expectation values for some observable from a fixed set of observables with precision epsilon and probability 1 minus delta in a, say, Park learning mindset? And how does that scale with the depth, the width, and the depolarizing noise as a kind of an ultimate limit to error mitigation in the worst case sense? And what we found was the following that surprised us a little bit. It turned out that the number of samples you need in worst case to do error mitigation scales like p to the power of minus omega n times d for mitigating depolarizing noise with a bound that sets in at log n depth. Whereas for non-unital noise, there is a similar statement for c to the power of minus theta nd with similar disclaimers in this size. So this means, I mean, that's innocent looking maybe, but it has pretty drastic consequences. So one needs of the order e to the power of omega n, that's the number, times depth, many samples for mitigation. So what was previously thought that this would be exponential only in the depth, but since in the NISQ regime, d is of the order log n, our results are exponentially stronger, which can be seen as a challenge for variational algorithms. So in a nutshell, already at log depth, and there's the mathematician's joke that log is upper bounded by 4. And that's not such a bad joke if you think about this. I mean, plot it and wait until you hit 4. You have a pretty big N. Already at log depth, in worst case, there is an information theoretic obstruction against this family of error mitigation protocols. So this is, again, is in worst case, but this is a pretty strong limitation. It doesn't mean that it doesn't work in the near term, but you already have a kind of this obstruction at log depth against general error mitigation schemes in worst case complexity. So how does this work? I give some hints on the mindset of the proof. So in a way, we set up a learning problem that can be solved by error mitigation in the way that if you get a sample complexity bound for 1, you can infer a precise and rigorous sample complexity lower bound for the actual sample complexity problem. And the problem we set up is basically one that discriminates outputs of noisy quantum circuits where you feed in either computational basis states or the maximally mixed state, and then you get like Kullback-Leibniz type quantities of this kind where you see the output of the computational basis state or the output of the maximally mixed state where you do a measurement like a Pauli Z type measurement, and based on this what we call noisy state distinguishability, you get a sample complexity bound, and using that you get a sample complexity bound for the actual error mitigation task. And then taking this idea of inference seriously, this is like of the flavor of a multi-hypothesis testing problem where you want to see which of the computational basis state or the maximally mixed states you have had. And then you can formulate a variant of a Fano's lemma that any single sample test that distinguishes n+1 distributions, P0 to Pn, where the last one is the one that corresponds to the maximally mixed state, must fail with probability at least 1 minus alpha with a bound of this type that I mentioned here that involves sums of Kullback-Leibniz divergences. And the heavy lifting, the hard work in this proof is to stare at the right-hand side and to bound the right-hand side applied to the problem of feeding in a computational basis state or a maximally mixed state of a type to get the right-hand side to get this e to the power of n times d scaling of the type that I mentioned in the theorem. And then one has to get constructive and explicit and construct evil circuits, bad circuits, worst case circuits that have the right scaling and the right properties. And it turns out that it's sufficient to provide circuits for which the bound, this Kullback-Leibniz divergence, is enormous, it's huge. And for this, it turns out to be good enough to make the purity of the outputs of computational basis states small. But purities are polynomials of degree 2, the quadratic. So then we are in the realm of unitary 2 designs once again. And then you have to, one can see that there is circuits, random Clifford circuits that give rise to 2 designs already at polylog depth. At polylog depth. Yeah, and then you see that that you have an explicit circuit that's so short that is giving rise to the right purities that give rise to the right Kullback-Leibniz divergences. So these random circuits shift the purity contribution to larger weight Pauli words that are then more fragile to the noise setting in. You have sufficiently many of the large Pauli words to then get the right scaling in this Fano's lemma, to then get the right scaling in the sample complexity bound, and then get the sample complexity bound of the error mitigation protocol. But the careful observers here might see that this is where the worst case thing comes in. So we really think of random Clifford circuits, and to get a unitary 2 design here, you really have to be a bit all-to-all coupled. So that's a very non-local way of doing it. So if you want to improve this, here's your chance. So that's where the worst case flavor comes in, to have like a all-to-all coupled random Clifford circuit. But that's a fair worst case result that gives rise to the right scaling if put all together in the right way. So there's strong obstructions against error mitigation already at log depth. This does not constrain quantum error correction at all, but it does constrain meaningful families of error mitigation in a drastic way. It doesn't mean that error mitigation does not work. It just means it does not scale in the most drastic of all senses, and it does not work well for all circuits. It may well work well for some circuits. It will not scale, it will not work well for all quantum circuits. It also has many no-go results. I can tell many stories about no-go results. I will not for reasons of time, but there are always invitations to think outside the box. And this is already happening. There's some protocols that make use of more coherent use of data. We also have looked at ways of bringing together randomized benchmarking with classical shadows to give rise to a kind of error mitigated readout that is not affected by our theorem. Also last night, I looked at a poster that's actually together with one of the co-chairs of this conference that could be interpreted as a kind of coherent error mitigation type of in a way on purification protocols of a kind. So it does constrain error mitigation in a pretty strong way, but it's not the end of the story, and there's no reason to get depressed of a kind. To come to the last technical point, in fact, the impact of non-unital noise, and that came out of this project because we looked at non-unital noise altogether, can be much more drastic and crazy as we expected. And this is not a fully new question. Even this paper by Ben Orr-Gottesman from more than 10 years ago was contemplating this. Think of amplitude damping noise as the most paradigmatic of non-unital noise that cools down a system. And if you think about this, and if you use this, this can be a pretty cool and powerful resource because you can cool down systems and you can use this sink of entropy in error correction inspired protocols to do things better. So sometimes you can even use non-unital noise as a resource to your benefit, just to have in mind. So non-unital noise can be funny. I think the co-authors are partially here, thought what happens to quantum circuits if you apply them to non-unital noise. And then this became a long and winding paper with many results. For example, for a deep random quantum circuit, under any uncorrected, possibly non-unital noise, you get an effective truncation to log depth on average. That's important, which means if you have a very deep quantum circuit, just as well do the last log n bits and cut away the rest. Replace it by the identity and you're in business. Yeah, so you can do deeper circuits, but you will get, for better, you have log depth. For worse, you have log depth. It is what it is, so the other parts doesn't matter. They do not matter. That's kind of interesting. Actually, that's an on average result that's kind of important to contemplate. I was not so long ago giving a talk about something similar, and then actually the CEO of IQM Finland came to me and said, cool, that's nice, but I have a counterexample. And then we contemplated this, and we realized that he didn't appreciate that it's an average case result. Of course, you can set up certain settings where you can like swap things and beat it. On average, the last log n qubits do it, and that's it. There is log n, work with it. That's the insight. Then Barn plateaus are much discussed, for better or worse. I'm not sure how surprising I find that. Sometimes I find that very surprising, sometimes not. It's related to the fact that if you have a huge variational landscape, say if you have a quantum circuit and initialize this with a unitary tree design, then most of the time, if you have a local cost function, the variance of the cost function will be small, exponentially small, and the gradients will be very flat, which means if you want to go downhill and estimate gradients from data, you cannot because it all looks completely flat and you don't know where to go. That's the Barron-Plateau problem, which means you can't train quantum circuits if you just randomly initialize them. Of course, you can say then do something better about this. That's the topic of warm starting, don't get me going, but there's the obstruction to variational quantum algorithms called the Barron-Plateau problem. Here, there's good news and bad news. The good news is there is no Barron-Plateau problem. One can show that for local cost functions, the cost landscape is never flat and the gradient never vanishes under non-unital noise. Yay, great news. That was even the title of an early version of the paper, like there's no Barron-Plateaus for non-unital noise. That sounds great. This trainability question is kind of gone, but kind of for the wrong reasons, because you are not expressive enough and you're not powerful enough with your quantum circuit, and while you are trainable, it's largely due to the fact that you have log depth available anyway, and then you can train the few parameters that you have, and the others are made redundant by the noise effect that you have. In a way, there's no bar and plateau, but that's both good news and bad news at the same time. To add insult to injury, you can even classically simulate, on average, expectation values of every observable to additive precision with probability 1 minus delta at any depth with this sample complexity, which means that if you have constant precision, this gives rise to an efficient algorithm in any dimension, and for 1 over poly precision, this is efficient in 1 spatial dimension. But if you have a classical simulation algorithm that improves on earlier results along similar lines in the past, then you have like dequantized the quantum algorithm, and once you're in this setting, that's a pretty broad class of quantum prescriptions, you have a classical simulation algorithm for the circuit, and you cannot hope a quantum advantage to arise. So that's a pretty strong classical simulation method for expectation values of this type for non-neutral noise, so general noise, and that builds on the earlier results. Basically uses like effective light cones to dequantize a large class of quantum circuits as a kind of challenge to near-term quantum computing. I said I would not overrun in time. So non-neutral noise acts strikingly differently. It works very differently to non-neutral noise. It's also the actionable advice to think carefully about your noise model. It doesn't matter what you do. It's not unimportant. But at the same time, if you have a noisy quantum circuit, log depth is all you have. And sometimes you are even in the classically efficiently simulatable regime, taking away quantum advantage. So think hard of the resources that you have. 47 minutes, so it's a good moment to come to the showdown or the coda on the good, the bad, and the ugly. So in this talk, we set out to ask the question whether we can hope realistic quantum devices of the near future, of like soon or the near future, provide some sort of advantage over classical computers, not for practical problems, but for practically minded problems that have the right mind map of being like alluding at industry relevant problems of a kind. And along these lines, we saw good, bad, and ugly things. For example, we found that, yes, there are super polynomial advantages in Park distribution learning. That's great news. That's a super polynomial reduction for classical data in the right sense, albeit for unrealistic, like artificial data. Yeah, but then you ask, great, that's a good in principle result, but how much structure do we need? Machine learning is about pretty unstructured data. This is for structured data. That's not so clear. Also, we've seen that a single T-gate renders learning hard. It can be seen as an obstruction against near-term algorithms. At the same time, there seem to be constant depth advantages in constant depth quantum circuits over constant depth bounded fan-in gate classical circuits. We found strong or very strong limitations against quantum error mitigation already at log depth. Again, log is upper bounded by 4. So for very short circuits, there's already asymptotically a limitation against error mitigation. Again, it doesn't mean that error mitigation doesn't work. It just means it does not scale in worst case for all circuits. And that's something you have to have in mind. That's the limitation of the setting. And even more drastically, we found this effective log depth model in that you can, if you have a circuit, you can basically throw out everything and keep the last log n layers, and that's all you have, work with it. So we have to get used to the insight that in the near-term regime, without quantum error correction, logarithmically deep circuits is all that we have in pretty much all generality. Sometimes yet, and that's something I did not speak about, noise can help. So here we used ideas from classical machine learning to show that if you have over-parameterized quantum setting and you have saddle points, if you add stochastic noise, you can provably show that you go to the best local optimum nearby and overcome the saddle point problem. That's a kind of a proof. Even we put in data from the IBM Q machine, which is kind of cute because oftentimes you just generate a new plot. That's the same one, just looks a bit noisier. But here we had to ask the IBM Q machine whether the noise they actually have in the actual device fulfills the assumptions of our theorem. And it did. So we did go to the best local optimum in a way. We also found that symmetry can help. You can twirl over group symmetries in circuits, yawn, that's like so zeros, but you can also do this over the classical data. And if you exploit symmetry in classical data and quantum circuits together, you can do much better and you can improve the training of variation quantum circuits by using symmetry in the right way. Don't overdo it. See Andy Bauer here, he has found what happens if you overdo the symmetry thing. All this means, in particular the last part, that presumably in the long term we have to do quantum error correction. I must say that, for many years the NISQ regime was like the holy regime of getting advantages. It was a bit overhyped. And then suddenly people said, NISQ is over, now we do fault-tolerant quantum computing. I don't know. I mean, I find this a bit exaggerated. It was a bit overhyped before and a bit underhyped now. I do think that there's a lot of potential in near-term quantum computing, and we should also mathematically minded think about this. That said, in the long run, we have to deal with quantum error correction of a type. And I didn't speak about this to speak not about everything, but much of the efforts in our team is really about new types of quantum error correction. We thought a lot about Floquet codes with low-weight Pauli measurements, say two-weight Pauli measurements, GKP codes, finding good codes for continuous variable quantum systems, or QLDPC codes and decoders, which is something many people think about. I saw lots of posters yesterday on LDPC codes, where I guess the holy grail question is how to do quantum computing with that. We already found highly efficient decoders for QLDPC codes of this kind. Of course, the big thing is happening in experiments, yes, but it's highly insightful and exciting for theorists to think about quantum error correction protocols of this kind. Perturbative gadgets can help in barren plateaus to some extent. It's good in the near term, but again, it's rather bad news in the long term, because you can see that while it helps a little bit, it releases the pain to some extent. In the long run, asymptotically, the pain comes back. So perturbative gadgets are not the wonder weapon to improve variational quantum circuits. But then we had also had new insights into generalization and expressivity, or looked at single-shot machine learning that is a more like practically minded setting of thinking about machine learning altogether. At some point, we thought, getting a heart attack overnight, that we had shot down variational quantum machine learning. If we found like classical surrogates using a Fourier transform picture of variational circuits, where we could do sampling algorithms at the end and sample the output of the variational distribution on a classical computer, hence dequantizing it. But then the full story is more subtle than that, because you have, in training, you have to look at the functional dependence of the variation parameters and the sampling. So while the statement is true, there's a lot of fine print coming in, and we looked a lot at the fine print using random Fourier features in training variational circuits of this kind. So that's all very promising and all very nice. So it does seem to be true that it's meaningful, and we should think of practical applications of the machine learning, the optimization type. But at the same time, it seems presumably fair to say that for the years to come, when we think of near-term devices, we presumably have to think a lot about problems that are somewhat physicsally motivated, that are in the realm of quantum simulation, where you go into the lab and probe systems under highly precisely controlled conditions, say where you think of like curved spacetimes or something in the lab under conditions that are more precise than what was possible before. But again, there's a new twist to this when you think of notions of Hamiltonian learning that become so popular these days. When we started this, it was not popular at all, but after 5 years of pain, sweat, and misery, we calibrated the Google Sycamore chip, and this will come out anytime, hopefully next week or so, where you take data and based on snapshot data in time, learn very precisely Hamiltonian. But once you have precisely understood what Hamiltonian you have in the lab, you can take that data, run it, and make predictions. But now with much more predictive power, because you're not just running some experiment, but you're running a Hamiltonian that you very precisely know. And that simulation augmented with techniques of Hamiltonian, or for that matter, Liouvillean learning, give rise to a kind of an interesting way of thinking about analog simulation altogether. So can we hope noisy, realistic quantum devices to provide a speed up over classical computers? And my clear message of this talk is definitely maybe. And I announced that we also have a new round of postdocs and PhD positions available soon, so ask me about this. And on this note, I thank you very much for your attention. I'm looking forward to questions you might possibly have. Thank you very much.
Questions?
Thank you for a very interesting talk.
Thanks.
I have a question about the limitation on error mitigation. During your talk, you said that the exponential hardness appears at log depths. But what I was thinking was that if we consider like a global observable, I think it already global observable already has large Pauli weights. So I think that we can show exponential sampling overhead at constant depths. And do you have any idea about what I said?
Yes, I mean, well, what you say is presumably true. I mean, I think most people are probably mostly interested in local observables, and that's kind of the hard and the interesting bit. Although I think technically what you say is true. But I mean, it's true for pretty elementary reasons. I mean, like say, take a product state of n qubits, and then you take another product state that's very similar in trace distance locally, but is just tilted by some degree, and then this will be exponentially off from the previous one in n, right? I mean, you're right that if you look at global observables, they can be tricky and even harder, but I think the surprise value comes in that if you even already look at local observables, you get this. But what you say is right, which is yet another lesson to learn, which is if you think of global observables, you have to even think harder. That's right.
More questions? Okay, actually, I have one. Regarding the hardness of learning Clifford plus T, like at least one T. Okay, it's hard, like that's not to show, but do you have something that's non-trivial? Do you think that there's an algorithm that's much better than, I don't know, trying all possible Cliffords plus 1T gate?
That's a good question. Yeah, not really. I mean, in the end, it's kind of, I mean, it seems implausible that it's kind of hard. We have this kind of reduction that I mentioned. So ultimately, testing all possibilities is a way, and that gives rise to an algorithm. But this is not tight, so to say. But I mean, that's all we have. I mean, in the end, you have to check all possibilities, but we do not have any better algorithm than that. So you can't go back. Once you have the distribution, testing all possibilities is basically all you have. But then the forward direction is easy. You can simulate efficiently in constant depth. And you can weakly and strongly simulate forward, but that's all you have. It's kind of funny.
Okay. Any other question? If not, let's thank Jens again.
Okay, thanks.
Please don't move. We have actually we're going to give the prizes for the best, the outstanding paper awards right now. Can we
Maybe
Yeah, I put it here. You can just reload it.
Yeah, if it's always connected. So, wait, I need to connect and then.
Or connected.
So to connect, you need to.
So the first prize, outstanding paper prize, will go to the paper multi-qubit lattice surgery scheduling, where Alison Silva and co-authors got it. So is Alison here? Okay, come. And the second paper will be given to the second outstanding paper prize will be given to this paper, Stochastic Error Cancellation in Analog Quantum Simulation by Yi Kai and co-authors. Is Yi here? Okay, yeah. And now we can go to the coffee break.